Most of consumer theory I focused on deduction, starting with a utility function and deriving how a consumer should behave. We assumed the internal logic existed, then looked for the resulting demand. But in the field, we only have access to market data, the prices paid, the income available, and the quantities purchased. Theory 2 reverses the engine. We start with behavior and ask, can a single rational preference relation generate this data? This requires diving into 4 areas: the Slutsky matrix, revealed preference, exact welfare measures, and aggregation limits. We will find that the standard approximations used in applied work, like simple consumer surplus, often overlook the complex interactions between prices and income. If a demand system fails the test of integrability, we lose the mathematical bridge between observed choices and the actual well-being of the consumer. This is the Slutsky substitution matrix. We now collect the responses for every pair of goods into a single grid. The off-diagonal entries isolate the pure substitution effect, showing how demand changes when a price shifts once the income effect is stripped away. The first restriction is symmetry. Sij equals Sji. We prove this via the expenditure function. Since Hicksian demand is its first derivative, Slutsky terms are second-order mixed partial derivatives. By Young's theorem, the order of differentiation doesn't matter. They must be identical. The second restriction is that the matrix must be negative semi-definite. This property is rooted in the fact that the expenditure function is concave in prices. Because the Slutsky matrix is the Hessian of that concave function, it must satisfy the condition that V transpose SV is less than or equal to 0. The integrability problem asks, given an estimated demand system, could it have been generated by a rational consumer? This essentially runs the logic of theory I backwards. The integrability theorem states that if a system satisfies homogeneity, Walras law, symmetry, and negative semi-definiteness, a utility function explains that demand. We can use differential equations to recover the expenditure and utility functions that guided the consumer. Let's test a researcher's estimated demand system for 2 goods. We are given the price and income responses for both X1 and X2. We first solve for the substitution effect, S12, using the full Slutsky equation, getting 1.1. Then we solve for S21. Using the same method, the result is 0.4. 1.1 does not equal 0.4. Because symmetry is violated, we know this estimated model is misspecified. There is no rational utility function that could produce these specific responses. While the Slutsky matrix works for smooth, differentiable functions, applied economists often deal with discrete shopping baskets found in household survey data. The weak axiom of revealed preference, or warp, tests discrete data. If you chose bundle X0 when X1 was affordable, you must never choose X1 when X0 is available. Here, choosing X1 at 17 when X0 cost 11 is a direct warp violation. With 3 or more goods, a consumer can create indirect cycles of preference. The strong axiom, or SARP, expands the rule to cover these multi-step chains, ensuring there are no circular contradictions in the data. Afriyat's theorem is the bridge to empirical work. It proves that if a finite set of data satisfies these axioms, it is guaranteed to be consistent with the maximization of a well-behaved utility function. This leads to the revealed preference law of demand. It shows that price and compensated quantity changes move in opposite directions, a conclusion reached purely from the data, without needing calculus. By applying Afriyat's theorem, we can confirm the existence of a utility function solely from observed behavior, bypassing the need to assume a specific functional form. When we measure the welfare impact of a price change, we often use Marshallian consumer surplus, the area under the demand curve. But this measure is technically flawed because it doesn't account for how the change in price also changes the consumer's real income. This compares a standard Marshallian curve to a steeper Hicksian, or compensated curve. The gap between them is the income effect. The only time Marshallian surplus is exact is under quasi-linear utility, where the income effect is 0 and both curves perfectly overlap. Compensating variation asks what income adjustment at the new prices would keep the consumer at their original utility level. Equivalent variation asks what income change at the old prices would match the utility shift. Despite their different perspectives, for any given utility function, CV and EV will always result in the same numerical valuation of the welfare change. This distinction is critical for policy. Measuring the deadweight loss of a tax using the Marshallian curve can lead to significant errors. The calculation must be performed using the compensated demand curve. Failing to apply these Hicksian measures means that our estimates of the social costs of taxes or subsidies will be mathematically imprecise. These same principles apply to how we measure inflation. A Lasperi's index, like the CPI, tracks the cost of a fixed basket of goods from a base period. However, as the price of one item in that basket spikes, consumers naturally substitute toward cheaper alternatives. A fixed basket ignores this rational reoptimization. This leads to substitution bias. Because it fails to account for how consumers adapt, the Lasperi's index generally overstates how much the cost of living has actually risen. A true cost of living index would use expenditure functions to determine the minimum cost needed to reach a specific level of utility as prices fluctuate. Recognizing that consumers are active optimizers shows why tracking static baskets will almost always lead to an upward bias in inflation reports. So far, we've analyzed one consumer and specific goods, but most economic models aggregate millions of households and broad categories like food or housing. To group goods together, we require weekly separable utility. This is what allows for two-stage budgeting, deciding how much to spend on food and then how to allocate that food budget. For this to work, the way you trade rice for maize must be independent of how much you are spending on housing or clothing. Aggregating consumers is even more difficult. To treat a whole market as a single representative consumer, we need very specific conditions to hold across every household. This requires the Gorman polar form. For aggregation to be valid, the angle curves for every consumer in the economy must be parallel straight lines. Because these conditions are so restrictive and rarely found in real-world data, the representative agent used in many macro models is often a significant oversimplification. We have moved from the mathematical requirements of the Slutsky matrix to discrete tests for rationality, and finally to the challenges of measuring welfare and aggregating data. This table summarizes the core duality restrictions we have covered. Each equation represents a specific test of whether a demand system reflects rational choice. When solving problems involving the Slutsky matrix, the most common error is forgetting the income effect when calculating off-diagonal entries. Similarly, when calculating deadweight loss, remember that uncompensated Marshallian curves will give an incorrect result. The compensated Hicksian curve is the only reliable tool. To prepare for the live session, practice deriving CV and EV from a given expenditure function. Understanding the math behind these welfare measures is the key to mastering duality.